Hello everyone, welcome to my presentation today. My name is Hongyu. Today I'm going to introduce our work, Beta Oscillation Detector Design for Closed-Loop Deep Brain Stimulation of Parkinson's Disease with memristive spiking neural networks. I'm the presenter is the assistant professor in electrical and computer engineering at Michigan Technology University. I obtained a doctorate degree in Virginia Tech. Before that, I received my master's degree and bachelor degree in Missouri University of Science and Technology and Shenyang University of Technology. Here, in this slide, you can check my personal website. My research interest is neuromorphic computing, neuromorphic electrical circuit design for artificial intelligence, and artificial intelligence applications in robotics and medical device. This is the outline. First, today I would first introduce the background of deep brain stimulation of Parkinson's disease treatment. After that, I would talk about the how to apply neuromorphic computing to a closed-loop deep brain stimulation system. Next, I also will introduce how to build an animal model of Parkinson's disease using rats. The beta oscillation from the PD rats will be used for training our spiking neural networks to detect the symptom of Parkinson's disease. Then at last, we will introduce the conclusions. The deep brain stimulation, short for the DBS, is used for Parkinson's disease treatment by sending electrical pulses to the brain using a battery-powered implant DBS device. This device usually placed in the chest. Okay. The main features of the DBS system is firstly contains 24 hours and 7 days operation. And if it stops, the PD symptoms appear again. It's an implant device, and the frequency and the magnitude of the stimulus pulses are fixed. All these features lead to some drawbacks, such as the unstopped signals will join the battery shortly. Replacement of the battery requires a surgery. Okay, and long-term stimulus signals cause side effects such as the depression. So in order to deal with these drawbacks, a closed-loop DBS system is proposed, as shown here in this figure. The closed-loop DBS will monitor the signals from the brain to recognize the current level of symptoms of the PD, Parkinson's disease. With different levels of symptoms, the optimized stimulus signals will be sent back to the brain for PD treatment. So through this method, the closed-loop DBS can optimize the stimulus signals to reduce the power consumption and the side effects. In the closed-loop DBS system, there are several challenges. The first one is how to precisely monitor the states of the PD symptoms. And the second one is to use high energy efficient computational devices to generate optimized stimulus signals. In order to deal with these challenges, we will use beta oscillation signals as the biomarker of different levels of PD systems. And the neuromorphic computing is used for detect these levels. So here, the figure shows we use autogenetic technique to collect brain signals. This figure shows two levels of beta oscillation signals. The orange one has low power, shows is the health state, and the blue waveform shows a relatively higher power during the beta oscillation range, which indicates severe PD systems. After that, all the beta oscillation signals will put into the input into the neuromorphic computing system, combined hardware and software. In order to get a high level of beta oscillation signals, we build a PD animal model using rats. First, we inject neurotoxin into a specific region named medial-forebrain fungal, short for the MFB. Then the neurotoxin will kill specific neurons in this region to make the rats have the Parkinson disease. After that, a virus will inject into the STN this region. The virus carries a specific light-sensitive option to target specific neurons in this region, STN region. Through the autogenetic technique, the brain neurons will become active to the specific wavelengths of light. After building the PD model, we can collect the actual beta oscillation signals. In our experience, the light poles are used for providing DBS stimulus signals here, and another electrodes here is used for capturing beta oscillation signals. The detailed experimental setup is shown here. The autogenetic machine will send the light pulses to the PD mouse under test using this optogenetic fiber. And the beta oscillation signals will be analyzed by our data acquisition system. The measurement results show the PD rats under DBS signals have much smaller beta oscillation signals. The next step is to train spiking neural networks with beta oscillation signals as input to make these spiking neural networks recognize the PD symptoms. The spiking neural networks with the threshold functions cannot be trained since they do not have the derivatives. Here we use a specific method named Whetstone to overcome this issue. In Whetstone, at the beginning, the activity functions at neural networks are traditional nonlinear activation functions, such as bounded nonlinear function. But during the training process, these activation functions will be gradually converged into threshold function. Then the final delivered neural networks will only have threshold functions. So the training results are shown in this table. In this paper, we only use a small size of neural networks and limited data. So the inference and the training accuracies are relatively not very high. But in the future, we will generate more beta oscillations data. Hope the learning accuracy and the inference accuracy will be higher later. Moreover, we also design a circuit implementing the sharpening process in Whetstone. The sharpening neuron design consists of two parts, the current neural parts and the control module. In this circuit design, the input and output relationship can be controlled through these three control signals. As shown here in this figure, we can see that different combinations of input control signals, the slope of the waveform are different. Through this way, we can gradually change the slope from the traditional nonlinear active function to a step function or threshold function. After training spiking neural networks using Whetstone to recognize the beta oscillation signals, we extract all weight values and deploy them into a system-level simulator named NeuroSIM. The NeuroSIM can assign different devices for storing weights of the neural networks, such as traditional 6T, SRAM, and memristors. NeuroSIM can estimate the critical parameters for performance evaluation, including design area, latency, and power consumption. This is the comparison result between memristive synapse and 6T SRAM. The simulation result shows that the chip area, latency, and the power consumption of a detector using spiking neural network and memristive synapse reduced by 67.3 central percent, 14.1.9 central percent, and 11.7 central percent. In sum, our work for the first time apply neuromorphic computing on the closed-loop deep brain stimulation for Parkinson's disease treatment. Specifically, we use beta oscillation as the biomarker indicating the levels of the Parkinson's disease. The neural networks are trained with this beta oscillations data. The improvement of spiking neural network-based closed-loop beta oscillation detector is evaluated by NeuroSIM simulator. The chip area, latency, and power consumption reduced by using memristive synapse. This is all reference we talked in this presentation. This work is sponsored by the National Institute of Health, Institute of Computing and Cyber Systems, and Michigan Technology University. At last, I'd like to thank my student, Zach, and my collaborator, Dr. Yu, and all audience for listening my presentation today. Please feel free to ask any questions. Thank you very much.